Hello everyone, thank you for joining us today. My name is Ed Chadwick and I'm a reader in bioengineering here at the School of Engineering in the University of Aberdeen. I'm going to talk to you today about advances in prosthetic devices for upper limb amputees. A particularly technical talk. It's more to give you a sense of the activity in the field and just introduce you to some of the things that we do here in the university in terms of our research in this area. But before I start, I just wanted to introduce myself. So I'm Ed Chadwick. I'm a mechanical engineer originally. I did my first degree in mechanical engineering at the University of Nottingham. I then went on and did a PhD in bioengineering at Strathclyde. And I'm now part of the Theoretical and Applied Mechanics group here at Aberdeen in the School of Engineering. In terms of my roles, I'm the program coordinator for our MSc in Biomedical Engineering, and I'm also leading the research lab in bioengineering in terms of the rehabilitation engineering, including biomechanics and assistive technologies. And prosthetic devices comes under that heading, really. So just to give you a bit of background, a bit of history, I wanted to introduce you to a few different types of prosthetic devices that have been available through the ages and are still available in some cases. If we look at this figure over here on the left, you can see a mechanical hand that goes all the way back to the 16th century. So this is by no means a new topic. People have been trying to design effective replacements for people with limb loss for a very, very long time. The picture in the middle is a body-powered prosthetic limb and this is from the Science Museum collection. And this design is probably several decades old. This one probably goes back 60 or 70 years. And this is a body-powered prosthesis whereby movement around the shoulders causes the end effector, which in this case is a split hook, to open and close, allowing the user to pick up objects and manipulate objects, giving them back some of the function that they might have lost through losing their limb or perhaps being born with a limb difference. This consists of a metal end effector and some leather and plastic components in the harnessing system. If you look at the picture on the right, we can see a modern equivalent of this, and this is from Otto Bock. This is a split hook end effector for a prosthetic device. And you can see if you compare that one to the one in the middle that there's really very, very little change. Although that's a modern device, it looks almost identical to the older one. So those are body-powered devices. We can also think about cosmetic prosthetic devices. So on the picture on the left, we've got some examples of cosmetic prostheses from Steeper. So these may not necessarily be functional, but are there simply to replace the missing limb from an aesthetic point of view. So there's something there, although it may not actually be used for functional activities. In the middle, we've got a myoelectric hand from Otto Bock, and this is something which contains electric motors, so the hand will automatically open and close based on signals measured from the remaining limb of the user. And that's called a myoelectric hand. On the right, we've got a fairly modern interpretation of that. This is actually not really an available device yet. This is a research device called the Hannes hand. It's only just been designed and developed. It's a very interesting, very nice device, I think. Again, it uses a single motor to achieve opening and closing of the hand, but by intelligent design of the mechanism, they're able to achieve lots of different types of functional grip with that single actuator, simply by having an intelligent mechanism within the hand, in that it conforms to different shaped objects as you pick them up and manipulate them. So those are some different examples of hands: body-powered prostheses, cosmetic, and myoelectric. So if we think about the different examples that we've just looked at there, we can categorize them into really cosmetic or functional, and then within that we might have something which is a very basic representation, all the way through to things which are so realistic that at first glance it's almost impossible to tell them apart from the natural hand and arm. And on the other side, we've got functional devices where we might be looking at something which is body powered, so the movement of the parts of the body that are still intact is used to control more distal or remote parts. Or we could be thinking about myoelectric, where we've got electric motors driving something which is a bit more like a robotic hand, and that's controlled by signals measured from the body, which take the form of electrical signals from the muscles. If we look at the state of the art in myoelectric hands, we can have a look at this multifunctional device, and this one in particular is from from OSSA, or what was formerly Touch Bionics, and this is called the iLim Ultra. This is a few years old now, but not very many. This is a really advanced, highly functioning device, which again is myoelectric, multi-articulating. Signals are measured from the remaining muscles in the residual limb of the person using this device, and those are used to turn motors on and off. And there are 5 individually powered digits on this. So it's got really high levels of dexterity, which almost replicate the movement of the natural hand. All of the fingers can be controlled individually. It's got articulations at each of the joints, which represent the natural intact hand. So really, really high dexterity is possible with a hand like this. And this is the state of the art. Now, it's quite an expensive, complex device, but a really nice development that has a lot of potential. In practice, though, if we look at what's commonly in use amongst prosthesis users, we don't see that many people using such advanced devices as that. What we see still are that people opt for a split hook prosthesis quite commonly. This picture on the left is from a newspaper in the US that describes a farmer that had an accident. It's worth having a look at the article that describes that. It sort of shows you how quickly you can be, your life can change with a slight lapse in concentration, and that's what this person describes that happened to him. So he's lost both of his arms just below. He's lost both of his arms just below the elbow, and so he's a bilateral amputee, and he's using 2 split hook prostheses. And those are very functional, and they're quite robust, and they can be used for lots of industrial activity. So people who are still in work often choose those. The person on the right of this slide is demonstrating a myoelectric device. So there's electrodes in contact with the surface of the skin over the remaining limb, and he's put that sleeve over his arm that attaches to the artificial hand. And then by contracting the muscles on either the front or the back of his forearm, he's able to send a signal to the motors in the hand to tell that hand to either open or close. And that's quite functional and robust as well. It doesn't have the dexterity of the more advanced hand that we just looked at, but a lot of people choose this because it's reasonably reliable. So if we think back about all the developments that have happened to artificial hands over the last decades and years, a number of advances have been made to make them a lot better and a lot more functional. So lighter and better performing materials have been used, so the hands can be stronger and more durable. If somebody's using them for industrial work, for example, they don't want to be replacing the components every 2 weeks because they're wearing out. So that durability is really important. We've also seen advances in 3D printed materials that have allowed more customized devices to be made at lower cost, so potentially increasing the availability of devices. And this device in the picture on the right is an example of that from the company Open Bionics. We've seen more what we might call biomimetic design, so where the design mimics the natural biological system, leading to increased individual finger dexterity. So the iLim is an example of that. The Hennis hand with the intelligent mechanism is another example of that. That again tries to move towards increasing functionality, trying to give people back something which is more akin to the function that they might have lost through the loss of their limb if they're an amputee. We have also seen some improvements in autonomous control of some devices. So for example, if you pick up an object and you want to ensure that you don't drop it, then you need to be able to control how hard you squeeze that object, but not squeezing too hard such that you damage it. So some designs of artificial hand have that control built in, where the hand itself takes care of that and the user doesn't have to worry too much about that. We've seen some advances in control where the grip pre-shaping occurs as we move towards picking up an object, which also facilitates the use of that device. We've seen improvements in the cosmetic design of prosthetic devices, so cosmesis is better than it used to be, and that can mean more natural looking hands where, for example, as I said at the beginning, there are some designs where the design in terms of the cosmesis is so good that at first glance it's almost impossible to tell the difference with, you know, realistic nails and hair on the back of the hands, and the skin creases and so on are rendered very, very realistically. But actually there's been an interesting development in the other direction in the last few years as well, where hands are deliberately designed to absolutely not look natural. And again, this image on the right from Open Bionics is a good example of that, where they've taken the approach of actually designing prosthetic limbs for children, where they can choose their preferred superhero design. And that's a really interesting development as well, I think, sort of enabling children to be more confident in the use of a device which might set them apart from their peers and make them feel worried about using it. And the idea of this is that it gives them more confidence and increases their adoption of this kind of technology, which ultimately improves their quality of life. So that's an interesting development as well, I think. We've also seen artificial devices get stronger, so the increased strength of materials allows the device to then manipulate heavier loads and be used for a wider range of tasks. But in order to facilitate that, we had to wait for battery design to improve the battery life of the devices in use, so that you're not having to recharge them every 30 minutes or something like that. So lots of advances have taken place over the last few years, which have improved the design and the functionality and the accessibility of artificial hands or prosthetic hands. But really, control is still a key issue. I showed this nice iLimb device that's got individual movement of all 5 fingers and all the different parts of the digits in each finger. But how do you control that? What's the interface between the device and the user that allows the user to tell the hand what they want it to do? So if we look at the current methods for control in myoelectric devices, what happens is that there's an electrical contact between the socket and the residual limb of the user, so an electrode makes contact with the skin. As the user then contracts the muscles in their residual limb, those muscles produce an electrical signal, and that's picked up by the electrode, and that's then converted into a signal sent to the motors in the prosthetic device, in the myoelectric device, that tells that artificial hand to open and close or do some other function. So that's the means of control. And it might be as simple as opening and closing. So contract the muscle on the back of the arm, the hand opens. The muscle on the front of the arm, the hand closes. It could be that that's proportional. So the harder you contract that muscle, the faster the device moves. If you are lucky enough to have a multifunctional device that has the potential for using different grips, then those 2 signals are not going to be enough, because you have to not only open and close the hand, but you have to tell it which grip you want to be controlling. So it might be that you do some co-contraction or a double clench or something like that to switch from one mode to another, to move the hand fingers versus moving the thumb, for example. And there are some developments in pattern recognition whereby you might have more than 2 electrodes, so you might have 5 or 6 electrodes around the interface between the socket and the residual limb. And then there's a controller which recognizes the type of grip you're trying to make by learning the patterns that you make with those contractions across those muscles. And those different modes are suitable for different types of people, and in some cases they give quite good control and reasonable function. But it's not quite the fluid, natural dexterity of the natural hand, which is what a large number of prosthesis users say they want. Okay, they want normal function. They want to be able to do things fluidly and naturally without having to make awkward maneuvers. So, for example, they don't want to have to reach across with their other hand and manually move the wrist around, which is something that you see quite often. You see people reaching across with the one hand to the artificial hand and manually positioning the thumb so that they can then open and close the fingers and achieve the grip they want. That's not really quite natural and fluid. So in terms of the key challenges for the future of prosthetic devices, control is one of the most important things, natural control. How do you, as a user of a prosthetic device, tell the hand, which is an artificial motorized device, what you want it to do? Going the other direction, we with our natural hands have a sense of feedback. We have a sense of proprioception and touch. We know what our hands are doing without looking at them. We can feel how open or closed our hands are. We can feel if we're making contact with something, and we can feel how hard we're squeezing it. That's something that's completely missing for users of prosthetic devices at the moment. And so being able to add that in would really take control to the next level. And that would give us much better integration with the neuromuscular skeletal system between the device and the human system. And that integration is really key, and that allows that control to be taken to the next level. So one of the things that we're doing in our research is looking at the possibility of using a biomechanical model to enable control. So a biomechanical model, or a musculoskeletal model, is a model of the musculoskeletal system in mathematical terms that allows us to understand the relationship between the structure and the function of the human musculoskeletal system. So, for example, if I send a signal from my brain to my muscles, I know that the muscles contract and generate force. That force is applied to the bones and causes movement, and that allows me to interact with the environment. If I can simulate that system computationally and mathematically, then I can use it to understand better the relationship between those different aspects, and I can use that to improve the control of the prosthetic devices. So I could measure the descending signal coming down my arm by measuring the electrical activity of the muscles, but rather than applying that directly to the motors and telling them to open and close, I could simulate what my missing hand would have been doing if it was still present, and then get my artificial hand to do the same thing. So we're looking at seeing if we can use this approach to improve the control of prosthetic hand function. And the link on the slide here will take you to a recent article if you want to read more about that. I'm just going to very quickly show you some results from the lab that we took some time ago. The picture on the top left shows the sensors attached to the arm, recording the electrical activity of the muscles, and the signals that we get out of those sensors is shown in the graph directly below that. Those electrical activities are then passed to the computational or biomechanical model, represented by this hand with the red lines on it. And we calculate, we simulate and predict what the movement of the hand would be based on those electrical activities. We then get our development platform here, which is a desktop test robotic hand, to make those same movements, and then we can evaluate how good our control is. So the video that you can see playing here shows recording of the electrical signals in the arm being used to control the movement of an artificial device. And it's important to note that we are only measuring the electrical activity of the muscles. We're not measuring the movement of the person's hand at all in this approach. So that's one of the areas of research that we're involved in the School of Engineering here. One of the advantages of this approach is that we have a model of the muscles in the missing hand. So we're not just going straight from the measurement of electrical activity in terms of pattern recognition and trying to predict what the movement is. We're actually simulating what's happening in the muscles in between that as well. And that means we can generate additional artificial signals to provide that feedback back to the user, so the sense of what the hand is doing, which is called proprioception. We can actually simulate that as part of our model and use that to give the prosthesis user more of a sense of what the hand is doing. So the control can then become bidirectional. And not only are you telling the hand what you want it to do, but the hand is also telling you as a user what it is actually doing. That gives us true closed loop control, and we hope ultimately will lead to more natural control of advanced prosthetic hands. So if we go back to our classification of different types of devices that we had at the beginning, then we can see that I've added another box onto here. So we've not only got cosmetic and functional devices now, but I'm actually thinking about trying to take this to the next level and saying that we're going beyond just functional, but having something which is more embodied. So because of that feedback aspect and the natural control, the prosthetic user can feel like that device that they're using is no longer a tool that is something that they're holding and using, but actually is a replacement for the hand. It becomes a body part, it becomes embedded, and gives them a better sense of a device that they can actually do something more meaningful with. So my key message really when talking about all of these, apart from the details of the prostheses themselves, is to give you some insight into bioengineering as an interdisciplinary topic. So in order for us to achieve viable solutions to clinically important problems, we really need to recognize that biomedical engineering or bioengineering is an interdisciplinary topic. And so we're not just thinking about this in isolation as engineers, but we're working with end users, clinicians, scientists, designers, and others to produce a solution which is going to be really, really viable and useful to people. Because ultimately that's what we're trying to do. As engineers, we're problem solvers, and we want to make sure that we're solving important problems and providing solutions that are actually viable and useful as well. So I'll leave it there, but I just wanted to leave you a few things to think about, not necessarily about the technology aspects, but the sort of bigger picture of the prosthetic devices. Obviously, if we're talking about interfacing more directly with the musculoskeletal system and the nerves, as we go into something which becomes a more invasive product rather than something that you just put on, that increases the risk. What's the trade-off between the benefit that you get from increased function and the potentially increased risk that you're exposed to? Not necessarily for us as engineers to answer, certainly not in isolation, but useful things to think about for thinking about the future of devices and how we design them. In terms of the control, I talked about recording signals from the arm about the electrical activity of the muscles. Is it better to go higher up the arm, more towards the brain, and record those signals more centrally? Or should we record them as far away from the brain as possible, as close to the point where they're used in the hand as possible? There's a sort of neuroscience as well as an engineering aspect to that that's interesting to think about. How important are the cosmetic aspects of prosthetic technologies? And finally, in theory, because we're designing an external artificial device, we could provide function that exceeds the natural function of the normal hand. So I've got an intact natural hand. I can produce a grip force that is a certain amount. If I had an artificial device, I could theoretically provide something that provides double the grip. Is that something that we want to do or should do? These are just some of the broader questions that I think it's useful to think about. So I hope that's been a useful overview and insight into some of the important aspects of prosthetic technologies, some introduction to some of the research that we do in the School of Engineering here at the University in Aberdeen, and some idea of some interesting questions for you to go away and think about. If you have things that you'd like to talk about now, I'm happy to try and answer any questions. Just pop them in the chat and we'll come and discuss those in a minute. Okay, so thanks for joining us and thank you for your attention. Okay, so I can see that there's a couple of questions popping up in the chat here. So the first one is, as an engineer, how much medical expertise do you need to work in biomedical engineering? Well, that's a good question. I am an engineer, as I said, I'm a mechanical engineer. I'm very much not a medic, so I understand some of the broader issues around the use of medical devices. I have some understanding of the physiology and some of the potential clinical solutions to problems and the origin of the problems in some ways, but I'm not a doctor, and there isn't any need for biomedical engineers to be experts in everything. As I've said, it's interdisciplinary, so we work with different team members. So I work with medics and therapists, for example, in the development of new devices. If you were to do a course like an MSc in biomedical engineering, for example, if you came into that course as an engineer with, let's say, a mechanical or electrical engineering background, then you would do some courses as part of that program in basic medical science. So the important thing is communication. So you need to be able to communicate with people from different disciplines, but you don't necessarily need to be an expert in all the disciplines. So the next question is, out of all the prosthetic types that you've discussed, which would you say is the most popular in amputees? Without having access to accurate statistics on that, that's a very hard one to answer. I think it depends very much on the individual. And this is an important message as well, actually, I think, is that the solutions in biomedical engineering are very much patient-centered, patient-specific. So if you're an elderly person who's not particularly active, for example, maybe you've had an amputation as a result of some vascular disease or something like that, and you don't engage in particularly high load activities, then you might be happy with something which is more towards the cosmetic or lower function end of things. If you're a young person who's lost a limb through being in combat situation, for example, then you might have higher demands on a prosthesis, and you might choose something which has some level of function, but primarily is very robust. I think it's all down to the individual. I think there's a broad spread of what people prefer and what's available. I think ultimately, though, it comes down to what's the cost-benefit ratio, and cost in the broadest sense of the word there as well. I don't just mean financial cost. If something is awkward to use, difficult to maintain, uncomfortable to wear, and doesn't provide particularly high function, you're much less likely to use it than if the function is good and the threshold to using it, or the barriers to using it, are quite low. So another question I've got here is, what career opportunities are there in biomedical engineering? Again, it's a broad field. So I think, if I think about our master's course, for example, our master's course has been designed with the framework of the Institute for Physics and Engineering in Medicine in mind, where they've tried to help the development of courses that have a reasonably broad destination for graduates of those courses. So that means you might be going into research. So I've talked about some of the research today. So that might mean research in an academic environment in a university, or it might mean research in more of an industrial R&D setting. So you could be working in a company on the research side of things, developing new products. You might be working as a project manager or product development manager in a company. So you might be somebody who's more at the interface between engineers and end users. So for example, if you're developing a new product, then you might need electrical engineers to work on designing the actual circuit boards that go into the product. Your end user knows what they want the product to do. They understand the clinical context. They understand the issues around the use of the device in a clinical setting or a home environment. And the biomedical engineer is often a useful person in between those two, helping to translate the requirements of the end user into detailed engineering specifications that the engineer can then design to, and then feeding back the developments in that area back to the end user. Finally, you might be interested in more in a sort of clinical engineering setting. So clinical engineering is a subset of bio or biomedical engineering as well, I would say, where you might work in a hospital more directly with patients. So you might be involved in, for example, rehabilitation engineering, designing custom solutions for patients with specific movement disorders and disabilities. Or you might be working more at the medical equipment end, which could include servicing or repairing or customizing medical equipment, or at the management end of the management and maintenance of medical equipment. So it's a very broad destination of careers, I think. If people want to get in touch afterwards, I'm very happy to have conversations. You can either do that by email. I can answer questions about our MSc program, for example, or about our research or research opportunities. Okay, so if we want to end it there, then that's fine. So thanks everybody for coming, and I hope it was useful.